Hello there, and welcome to the Sleep Well channel. I am so glad you have found your way here tonight. Perhaps your day was long filled with noise and light and endless demands on your attention. But all of that can fade now. This is a quiet place, a space at the edge of the day where you can let everything go. There is nothing you need to do, nothing to solve, nothing to hold on to. Your only task is to rest. So let your shoulders soften, let the muscles in your face relax, and feel your body grow heavy, sinking gently into the surface beneath you, held and supported. Tonight, we are beginning a journey. Not to a place you can see on a map, but into the vast, invisible landscape that holds our universe together. We are going to drift through the quiet and profound mystery of dark matter. It is a story, not of bright stars, but of the silent, unseen presence that gives them a place to shine. A story of gravity's gentle hand shaping galaxies from a substance we cannot touch or see. Or some of what you hear may be new. Some may feel as distant as the stars themselves. But you don't need to grasp it all. Just let the words wash over you like a gentle current, carrying you toward a calm and peaceful sleep. And just before we begin, if these quiet explorations of the cosmos help you find rest, consider leaving a gentle tap on the like button and subscribing. It helps other sleepy souls just like you find their way to this little corner of the universe. One thought at a time. Now, settle in. Let your breath find its own slow, easy rhythm. And let's begin our journey into the invisible cosmos. The stars you see on a clear night are only a whisper of what is truly there. When you look up into the deep, dark expanse, you see a scattering of brilliant lights, planets, distant suns, and the soft, milky river of our own galaxy. It feels vast, almost infinite, and yet all of it, every star, every nebula, every galaxy we have ever photographed, makes up only a tiny fraction of the universe's true substance. For every visible speck of light, there is an immense unseen ocean of something else. A quiet gravitational presence that fills the space between and within galaxies, holding everything in its gentle, invisible embrace. Scientists call it dark matter, not because it is black or ominous, but because it does not interact with light. It does not shine. It does not reflect. It does not cast a shadow. It is utterly, completely transparent. It is the great unseen majority of the cosmos. All the matter we have ever known, the stuff of planets and people, of dust and suns, is just the luminous foam on the surface of a deep, dark sea. To know this is to look at the night sky differently. It is no longer an empty darkness dotted with light, but a full, rich space whose greatest secrets are kept in silence. The universe is not empty. It is just shy. We know this invisible presence is there not by seeing it, but by feeling its touch across galaxies. In the great spiral cities of stars like our own Milky Way, everything is in motion. Stars orbit the galactic center in a slow, cosmic dance that takes hundreds of millions of years to complete. According to our understanding of gravity, stars on the outer edges of a galaxy should move more slowly, like planets farther from the sun, and yet they do not. When astronomers first measured their speeds, they found something astonishing. The outermost stars were moving just as fast as those closer in. They were racing along at speeds so great They should have been flung off into the void, scattered like sparks from a spinning wheel. But they were not. They remained in their orbits, held steady in a gravitational grip far stronger than all the visible stars could provide. Something else was there. Something unseen, yet massive, wrapping the entire galaxy in its weight. This was the first quiet clue, the first whisper from the invisible world. It told us that galaxies are not just what we see. They are cradled in enormous, invisible halos of dark matter, whose quiet strength keeps the stars from wandering away into the intergalactic night. This silent matter does more than just hold galaxies together. It bends light itself. According to Einstein's theory of relativity, massive objects warp the fabric of space-time, and light, as it travels through the cosmos, follows these curves. Imagine a heavy ball placed on a stretched sheet, causing it to sag. A marble rolled nearby will curve its path as it passes the dip. In the same way, the immense mass of dark matter gathered in and around galaxy clusters creates gravitational valleys in space. Light from even more distant galaxies, traveling for billions of years, will bend as it passes through these regions. From our perspective on Earth, this bending can distort our view of the cosmos, creating strange and beautiful illusions. We might see the light of a single distant galaxy stretched into a luminous arc, or smeared into a ghostly ring, or even appearing in multiple places at once. This phenomenon is called gravitational lensing. It is a gift to astronomers, for it allows us to map the invisible. By observing how light is bent, we can calculate the location and amount of the dark matter that is doing the bending. In this way, the universe provides its own tool for seeing the unseeable. We trace the contours of the darkness by watching how the light dances around it, revealing the hidden architecture of the cosmos, one gentle, distorted echo of starlight at a time. This strange new substance is not dark in the way a shadow is dark. A shadow is simply the absence of light, a space where light has been blocked. Dark matter is something else entirely. It does not block light. It does not absorb it. Light passes through it as if it were not there at all. It is the ultimate form of transparency. If you were holding a sphere of pure dark matter in your hand, you would not see a dark ball. You would see nothing at all. Your hand would appear empty, and yet you would feel its weight. This is the central paradox of dark matter. It has mass, it has gravity, but it is immune to the force that illuminates our entire world, electromagnetism. This is the force that allows us to see, to touch, to feel the solidity of objects. It is the force that makes a wall feel solid, that makes the sun shine, that carries the radio waves that connect our world. Dark matter does not participate in this force. It feels no friction. It knows no light. It is a separate kind of reality, interwoven with our own, but interacting only through the slow, steady pull of gravity. It is the ghost in the cosmic machine, a presence defined only by its weight, forever separate from the bright, colorful world we know. And so it is important to remember that dark matter is not simply empty space. The vacuum of space is something different. It is the baseline of our universe, a near-perfect emptiness, though even it hums with the faint energy of quantum fluctuations. Dark matter, however, is a substance. It is thought to be made of particles just as the world we know, is made of protons, neutrons, and electrons. We do not yet know what these particles are, but we know they must be all around us. As the Earth orbits the Sun, and the Sun orbits the center of the Milky Way, our entire solar system is moving through the vast, invisible halo of our galaxy's dark matter. This means that at this very moment, as you lie here breathing softly, billions, perhaps trillions of these silent particles are streaming through you. They pass through the walls of your room, through the bed beneath you, and through your own body, without ever touching a single atom. They are like a constant gentle rain that you will never feel a river of unseen matter flowing through everything. There is no shield that can stop it, for there is nothing to stop. It is a quiet reminder that we are porous to the universe in ways we can scarcely imagine, forever bathed in a current that began its journey long before our world was even formed. In the language of cosmology, this unseen substance is often described as cold. This does not refer to its temperature in the way we might think of a winter's day. In this context, cold means slow-moving. In the early universe, when everything was hot and dense, these dark matter particles were not zipping around at near the speed of light. Instead, they were drifting, moving sluggishly. And this slowness was crucial. Because they were slow, gravity could gather them. While hot, fast-moving particles of normal matter were being pushed around by radiation, the cold, dark matter began to clump together, forming the first small pools of gravitational influence. These were the seeds, the quiet, invisible anchors around which everything else would eventually form. Over millions of years, these dark matter clumps grew larger, pulling in gas and dust, which then collapsed to form the first stars and the first galaxies. Dark matter was the patient architect of the cosmos. It built the framework, the hidden scaffolding, and then the luminous matter we see today simply settled into the structures it had already prepared. Without this cold, slow beginning, the universe might look very different. A diffuse, unstructured haze of gas with no galaxies, no stars, and no planets. The great, brilliant structures of the cosmos owe their existence to the quiet, patient work of a substance that moved slowly through the darkness, allowing gravity the time it needed to build a home for the light. Beneath the glittering cities of stars, and woven through the vast, quiet spaces between them, lies a hidden map. A blueprint drawn not in ink, but in gravity. This is the great and silent architecture of the cosmos, a structure built by dark matter upon which everything we see has been arranged. When we look out with our telescopes, we see galaxies clustered in beautiful, intricate patterns, some in tight knots, others strung out in long, delicate chains. For a long time, this arrangement seemed almost random, like jewels scattered on black velvet. But now we understand that these patterns are not accidental. They are the visible signs of an invisible framework. The galaxies are not floating freely. They are following the contours of a landscape we cannot see settling into the gravitational valleys and along the cosmic ridges carved by dark matter over billions of years. Imagine a vast dark garden where the soil itself is made of this unseen substance. The flowers and trees, the luminous galaxies can only grow where the soil is rich and deep. The cosmic web is this garden. And dark matter is the soil from which all the light has sprung. Every great galaxy, including our own Milky Way, is thought to lie at the heart of an immense spherical cloud of this invisible matter. This is its dark matter halo. It is not a ring or a shell, but a deep, diffuse sphere of gravitational influence that extends far beyond the galaxy's visible edge. The spinning spiral of stars we see is just the bright, compact center of a much larger, much more massive structure. This halo acts as a cosmic cradle, a nest woven from gravity. It was the first thing to form a gentle gathering of slow-moving dark matter in the early universe. And once it was in place, it began to pull in ordinary matter, the hydrogen and helium gases left over from the Big Bang. This gas, drawn into the center of the halo's gravitational well, began to swirl and cool, eventually collapsing to form the first generations of stars. The halo, then, is both the galaxy's foundation and its guardian. Its immense mass provides the stability that the galaxy needs to grow and evolve, preventing it from being torn apart by the gravitational pull of its neighbors. It is a quiet, invisible protector, a ghostly cloak that holds the city of stars in a safe and steady embrace. Even now, it continues to draw in new material from the space around it, feeding the galaxy and allowing it to continue its slow, graceful process of creation. These halos are not isolated islands. They are connected, linked together by vast, thread-like structures that stretch across the universe. These are the filaments of the cosmic web. Imagine threads of spun glass, impossibly long and thin, crisscrossing the void. These filaments are made primarily of dark matter, and they act as the great highways of the cosmos. Along these threads, galaxies flow like beads on a string, drawn by the gentle, persistent pull of gravity. The filaments themselves are not uniform. They are denser in some places, thinner in others, and where they intersect, matter gathers in great knots. These intersections are where we find the largest structures in the universe. The superclusters of galaxies, sprawling metropolises containing thousands of individual galaxies, all bound together in a single gravitational system. The cosmic web is the largest pattern in nature. It is a structure that spans billions of light years, and it reveals a universe that is not chaotic, but ordered, connected, and woven together by an unseen hand. To trace the paths of these filaments is to understand that no galaxy is truly alone. Each is part of a grand, interconnected tapestry, its fate tied to the invisible currents that flow through the dark. And just as there are rivers, there are also empty spaces. In between the glowing filaments of the cosmic web lie the great cosmic voids. These are immense, almost perfectly empty regions of space stretching for hundreds of millions of light years. They are the quietest, loneliest places in the universe. While the filaments are teeming with galaxies, the voids are profoundly still. They are not entirely empty, of course. A few stray galaxies may drift through their centers, and they are filled with the same transparent sea of dark matter particles, just at a much, much lower density. But for the most part, they are great silent chambers in the cosmic architecture. The voids are just as important as the filaments in shaping the universe. Their low density creates a subtle outward pressure, helping to shape the flow of galaxies around them. Matter drains from the voids and gathers onto the filaments like water running off a high plateau into a network of rivers. In this way, the universe organizes itself into a beautiful foam-like structure, a delicate balance of the full and the empty, the dense and the diffuse. To contemplate a cosmic void is to gaze into a stillness so profound it borders on the absolute. It is a reminder that the universe is made not only of presence, but of absence, and that both are part of its grand and elegant design. The shape of this cosmic web, with its intricate network of filaments and voids, is not something that could have formed from ordinary matter alone. In the early universe, normal matter, the protons and electrons that would later form atoms was tightly coupled with light or radiation. It was tossed about on a sea of photons, unable to settle, unable to clump together under gravity. Radiation pressure pushed it apart as fast as gravity tried to pull it together. But dark matter was different. It did not feel this pressure. It was immune to the chaotic dance of light. And so while normal matter was being churned in the hot, dense fog of the early cosmos, dark matter was already beginning its quiet work. It began to collapse under its own gravity, forming the first small structures, the first invisible seeds. These seeds became the dark matter halos, the gravitational anchors that would later draw in the ordinary matter once the universe had cooled enough for the light to release its grip. Without dark matter, the universe would have remained a smooth, almost featureless haze of gas for much longer. The formation of galaxies would have been delayed, or perhaps would never have happened at all. Dark matter gave the universe a head start. It was the patient sculptor, working in the dark, laying the foundations long before the lights came on. And so the beautiful spiraling shapes of galaxies are in a sense a secondary creation. They are the visible consequence of an invisible process. The distribution of stars, the curve of a spiral arm, the gentle glow of a galactic bulge, all of these are shaped by the underlying landscape of the dark matter halo in which they sit. The halo's shape, its density, and its own slow rotation all influence the visible galaxy at its heart. If the halo is slightly elongated, the galaxy may form a bar of stars at its center. If two halos merge, the galaxies within them will eventually spiral together in a cosmic dance of creation and renewal. Astronomers who create computer simulations of the universe have found that they can only reproduce the structures we see today if they include dark matter. Without it, the simulated galaxies are too small, too disorganized, or simply don't hold together. Dark matter is the missing ingredient, the secret recipe that allows the universe to build the elegant, complex structures that fill our night sky. Every galaxy we see is a testament to this partnership between the visible and the invisible, a luminous island built on a foundation of pure, transparent gravity. The silent architecture is everywhere, holding up the heavens so that they do not fall. In the first moments of time, when the universe was younger than a single second, it was a place of unimaginable energy, a glowing uniform sea of particles and radiation expanding at an incredible rate. There were no structures, no stars, no galaxies, just a perfect, seamless fog. And yet, hidden within that perfection were the faint, almost imperceptible whispers of everything that was to come. These whispers were tiny random fluctuations in the fabric of space-time itself, born from the strange and uncertain laws of the quantum world. And as the universe expanded, these fluctuations were stretched to cosmic proportions. These are the echoes we can still detect today, imprinted on the oldest light in the universe. But for these whispers, To grow into the great structures we see now, they needed an amplifier. They needed the quiet, steady hand of dark matter. It was dark matter that first listened to these faint signals and began to build upon them, turning the faintest of quantum murmurs into the grand symphony of the cosmos. The oldest light we can see is a faint, gentle glow that fills the entire sky. It is called the Cosmic Microwave Background, or CMB. This light was released when the universe was about 380,000 years old, at the moment when it cooled enough to become transparent. Before that time, it was an opaque, glowing fog. The CMB is a snapshot of the universe in its infancy, and when we look at it with our sensitive telescopes, we find that it is almost perfectly uniform in temperature. Almost, but not quite. There are tiny, minuscule variations, patches that are a few millionths of a degree warmer or cooler than the average. These are the imprints of those original quantum fluctuations, the stretched out whispers from the first moments of creation. And these tiny temperature differences are the key to everything. The slightly cooler, denser regions had a little more gravitational pull, and it was here that dark matter began its work. Unaffected by the light and radiation that still pushed normal matter around, the dark matter particles began to drift into these slightly denser regions, gathering slowly, patiently, over thousands of years, amplifying the tiny gravitational differences into something more substantial. This process was like a slow, silent gathering in the cosmic dawn. While ordinary matter was still a hot ionized gas, a plasma tightly bound to photons, dark matter was already beginning to collapse into the structures that would one day become the scaffolding of the universe. It was able to do this because it does not interact with light. It felt no pressure from the intense radiation of the early cosmos. So, as normal matter was being smoothed out and held in place by this pressure, dark matter was free to respond to the gentle call of gravity. It began to form the first small, invisible clumps, the primordial dark matter halos. These were the first structures of any kind to exist. They were the gravitational seeds, the invisible anchors planted in the smooth soil of the early universe. Without dark matter, the tiny fluctuations in the CMB would not have been strong enough to gather matter quickly. The universe's expansion would have smoothed everything out, and the formation of galaxies would have been a long, slow, and perhaps impossible process. Dark matter provided the gravitational boost needed to get the process started, ensuring that the faint whispers of the beginning would not fade away into silence, but would grow into the chorus of galaxies we hear today. The moment the universe became transparent is known as recombination. It was then that the cosmos cooled enough for protons and electrons to combine and form neutral hydrogen atoms. Suddenly, light was free to travel unimpeded through space. For ordinary matter, this was a moment of liberation. No longer pushed around by photons, it too could finally begin to respond to the call of gravity. And where did it go? It began to fall into the gravitational wells that dark matter had already been patiently digging for thousands of years. The gas flowed into the centers of the primordial dark matter halos, creating dense clouds that would eventually ignite as the first stars. This is why the structure of the visible universe so closely matches the structure of the invisible dark matter. The luminous matter is simply following the map that dark matter laid out for it. The galaxies exist where they do, because that is where the dark matter halos were waiting. The cosmic web with its filaments and voids is the visible manifestation of a pattern that was first traced in the dark. The early universe was a two-part story: the quiet, patient work of dark matter, laying the foundation, followed by the dramatic arrival of light and normal matter, building the shining cities upon that foundation. The evidence for this ancient story is not just theoretical. It is written in the sky. When astronomers study the distribution of galaxies across the universe, they find subtle patterns that can only be explained by this interplay between dark matter and normal matter in the early cosmos. In the hot plasma, before recombination, pressure waves like sound waves rippled through the ordinary matter. These waves, called baryon acoustic oscillations, left behind a characteristic pattern, a preferred distance between clumps of matter, like the faint ripples on a pond after a stone is thrown. These ripples were frozen in place when the universe became transparent. Dark matter, which was not affected by these sound waves, formed its own separate pattern of clumps. Over billions of years, galaxies formed where both types of matter were dense, and when we measure the distances between galaxies today, we can still see the faint echo of those ancient sound waves, a statistical preference for galaxies to be separated by about 500 million light-years. This cosmic yardstick is one of the most powerful pieces of evidence we have for the existence of dark matter and for our understanding of how the universe began. It is a fossil of a sound that once echoed through the infant cosmos, a sound preserved in the very placement of the galaxies. And so, the quiet, invisible work of dark matter in the early universe was not just a passive process. It was an active, shaping a guiding hand that transformed a smooth, almost featureless universe into the rich, structured cosmos we inhabit. It took the faint, random noise of quantum mechanics and amplified it into the grand, ordered structure of the cosmic web. It provided the gravitational nurseries where the first stars could be born, ending the cosmic dark ages and filling the universe with light. Every star that shines, every galaxy that turns owes its existence to this silent partner, this substance that worked in the darkness to prepare a home for the light. When we look back at the faint glow of the cosmic microwave background, we are seeing more than just old light. We are seeing the blueprint of a creation story, a story where the main character was, and still is, completely invisible. The whispers from the early universe tell a story of patience, of gravity, and of a darkness that was not an emptiness, but a beginning. If this invisible matter is a substance, a fundamental component of our reality, then it must be made of something. Just as the world we see is built from a small family of familiar particles, protons, neutrons, electrons, the dark matter that fills the cosmos must also have its own constituents. The search for these particles is one of the greatest quests in modern science, a hunt for a ghost that has shaped everything we know. Scientists have imagined many possibilities, many candidates for what dark matter could be. And the leading idea for many years has been a type of particle that is as shy as it is massive. They are called WIMPs, which stands for Weakly Interacting Massive Particles. The name itself is a gentle description of their character. They are massive, meaning each particle carries a significant amount of weight, perhaps tens or even hundreds of times the mass of a proton. And they are weakly interacting, meaning they almost never touch the world of ordinary matter. They feel the force of gravity, and they feel another fundamental force known as the weak nuclear force. But that is all. To imagine a WIMP is to picture a cosmic hermit, a particle that drifts through the universe, feeling the gentle pull of galaxies, but passing through stars and planets as if they were empty space. The weak nuclear force is the same force that governs certain types of radioactive decay. It is incredibly short-ranged and, as its name suggests, very weak. This means that a WIMP would have to come almost into direct contact with the nucleus of an atom for any interaction to occur. And even then, the chance of such an interaction is fantastically small. It is like trying to hit a single tiny bell in a vast dark cathedral with a single tiny grain of sand thrown from miles away. The odds are almost zero. This is why dark matter is so elusive. Billions of WIMPs may be passing through your body at this very moment, but the chance of even one of them gently nudging a single atom in your entire lifetime is incredibly low. They are ghosts in the truest sense of the word, present yet utterly disconnected from our sensory world. Their only influence is their collective weight, the sum of their individual masses, which on a galactic scale becomes the dominant force of the cosmos. The idea of the WIMP is not just a random guess. It emerged from deep questions within particle physics long before we even knew for sure that dark matter existed. Theories that sought to unify the fundamental forces of nature, such as a theory called supersymmetry, naturally predicted the existence of new heavy stable particles that did not interact with light. When cosmologists realized the universe was filled with an unknown massive substance, these theoretical particles seemed like a perfect fit. It was a beautiful convergence of two different fields of science, a moment where the needs of the cosmos seemed to match the predictions of the subatomic world. This alignment is what physicists call the WIMP miracle. It suggests that if a particle with the properties of a WIMP was produced in the hot, dense aftermath of the Big Bang, the amount left over today after the universe expanded and cooled would be just right to account for all the dark matter we observe. It feels like a clue, a hint from the universe that we are on the right path. It suggests that dark matter is not some strange, exotic anomaly, but a natural and expected consequence of the laws of physics as we are beginning to understand them. These ghostly particles, if they exist, would be relics from the universe's first moments. In the fiery furnace of the Big Bang, all kinds of particles were created and destroyed in a chaotic equilibrium. As the universe expanded and cooled, heavier, unstable particles decayed away. But a particle like the WIMP stable and reluctant to interact would have frozen out. This means that as the universe grew larger and particles became more spread out, the WIMPs simply stopped finding each other to annihilate. What was left was a sea of these particles, a cosmic remnant that has been drifting through space ever since, slowly gathering into the halos that cradle galaxies. They are fossils from a time when the universe was less than a second old, carrying with them the memory of that primordial fire. Their existence today is a testament to their quiet, solitary nature. They survived simply by not participating, by remaining aloof from the constant interactions that shape the rest of the matter in the universe. They are the silent witnesses to cosmic history, their presence a steady, unchanging echo of the very beginning. The search for these particles is a study in patience. Since we cannot see them directly, scientists have devised incredibly clever ways to try and catch a rare, fleeting glimpse of their passing. One method is called direct detection. Deep underground in laboratories shielded by kilometers of rock from the noise of cosmic rays and other radiation, scientists have built detectors of extraordinary sensitivity. These detectors are often made of large crystals of a very pure material, cooled to temperatures just a fraction of a degree above absolute zero. The idea is that if a WIMP drifting through the Earth happens to pass through this detector, there is a tiny, minuscule chance that it will collide with one of the nuclei in the crystal. This collision would be like a gentle nudge depositing a tiny amount of energy, which would create a faint flash of light or a subtle vibration, a single quiet ping in the deep silence. For years, scientists have been listening, waiting for such a signal. It is a search for the quietest sound in the universe, the whisper of a ghost passing through a wall. So far, the silence has remained unbroken, but the search continues, a testament to our desire to finally meet the invisible substance that has been our constant silent companion throughout all of history. Another way to hunt for WIMPs is to look for the signs of their disappearance. Although WIMPs rarely interact with ordinary matter, they can interact with each other. If two WIMPs happen to meet, they can annihilate, converting their mass into a burst of energy and more familiar particles, such as gamma rays or neutrinos. This is the reverse of the process by which they were created. These annihilations would be incredibly rare, but in places where dark matter is thought to be very dense, like the center of our galaxy, or at the heart of the sun, where it might be captured by gravity, there might be a faint, steady glow of these annihilation products. And so, astronomers point their telescopes toward these regions, looking not for the WIMPs themselves, but for the faint, high-energy light that might signal their mutual destruction. It is like searching for a ghost by looking for the faint flicker of a candle it leaves behind. Some tantalizing signals have been seen: a mysterious excess of gamma rays from the galactic center, for example, but we do not yet know if these are the long sought-after signs of dark matter, or simply the product of other more ordinary cosmic processes. The hunt for the ghost continues in the brightest parts of the sky, as well as the darkest corners of the Earth. While the idea of a heavy solitary particle, like the WIMP, has long been a guiding light in the search for dark matter, it is not the only possibility. The universe is often stranger and more subtle than our first guesses. And so another candidate has emerged from the quiet depths of theoretical physics, a particle that is in almost every way the opposite of the WIMP. It is not heavy, but incredibly light. It is not a distinct billiard ball-like particle, but something more like a wave, a gentle, pervasive ripple in the fabric of space-time. This candidate is called the action. If WIMPs are like silent, heavy stones scattered through the cosmos, axions are more like a faint, continuous hum, a low cosmic note playing everywhere at once. They are a whisper, not a ghost. The axion was not invented to explain dark matter. Like the WIMP, it was born from a completely different question in particle physics. It was proposed to solve a deep puzzle in our understanding of the strong nuclear force, the force that binds protons and neutrons together in the heart of an atom. The mathematics of this force suggested a certain kind of asymmetry should exist in nature, but experiments showed that it did not. The axion was a theoretical solution, a new incredibly light particle whose existence would naturally cancel out this asymmetry, restoring a balance to the laws of physics. It was an elegant mathematical idea, a small, graceful fold in the fabric of reality. It was only later that cosmologists realized that if this particle existed, it would have been produced in enormous quantities in the early universe. And because it interacts so weakly with anything else, it would still be here today, a vast cold sea of these tiny wave-like particles, with enough collective mass to account for all the dark matter we see. It was another miracle, another beautiful convergence suggesting that the solution to a deep puzzle inside the atom might also be the solution to a grand mystery among the galaxies. To imagine a universe filled with axions is to think of space as a field, a substance that can oscillate like the surface of a still pond. In the very early universe, this axion field would have been displaced, pushed away from its lowest energy state. As the universe expanded and cooled, the field would have begun to oscillate, to ring like a bell struck once at the beginning of time. These oscillations are the axions. They are not individual particles in the classical sense, but collective excitations of the field, a coherent wave that flows through all of space. The energy of this wave is what we perceive as the mass of dark matter. Because axions are so incredibly light, perhaps 1 billion times lighter than an electron, there must be a staggering number of them to make up the mass we observe. The universe would be filled with a dense, cold cloud of these particles, all moving together, flowing like a great, slow, invisible river through the cosmos. This collective, wave-like nature makes axion dark matter behave differently from WIMP dark matter on very small scales, potentially creating finer, more delicate structures that astronomers are now beginning to search for. The search for the axion is as delicate and subtle as the particle itself. Since axions are not massive enough to leave a clear signal, by bumping into an atomic nucleus, scientists must look for a different kind of interaction. The theory that predicts the action also predicts that in the presence of a very strong magnetic field, an axion can, on very rare occasions, transform into a photon, a particle of light. This is the key. The search for the action is a search for a faint, almost imperceptible glimmer of light appearing from nowhere. In experiments around the world, physicists have built devices that are essentially very sensitive, very quiet radio receivers placed inside incredibly powerful magnets. They are trying to tune into the frequency of the action's conversion. It is like trying to hear a single pure note in a universe full of noise. The signal, if it exists, would be unimaginably faint, a whisper of a photon that signals the presence of the vast unseen axion field. The experiments are called haloscopes because they are designed to look for the particles that make up the galactic halo. It is a search that requires immense patience and a belief that even the most subtle of cosmic secrets can be coaxed into revealing itself if only we build an instrument quiet enough to listen. If axions are the dark matter, then their wave-like nature could leave other, even stranger fingerprints on the cosmos. Because they are so light, they behave more like waves than particles on galactic scales. This means that instead of forming sharp, dense cusps at the centers of galaxies, as some models of WIMP dark matter predict, an axion halo might have a smoother, softer core. The center of an axion-dominated galaxy might be less of a spike and more of a gentle swell. Astronomers are peering at the centers of small, faint dwarf galaxy systems that are thought to be almost entirely dominated by dark matter, to see if their structures match the predictions of these wave-like models. The evidence is still unfolding, but these tiny, fragile galaxies may hold the key to understanding the true nature of dark matter. They are the quietest laboratories in the universe, where the subtle effects of this invisible substance can be seen most clearly. Furthermore, these ultralight axions could form strange and exotic objects known as axion stars or Bose-Einstein condensates. In these structures, an enormous number of axions would all fall into the same quantum state, behaving like a single giant particle. An axion star would be a dense, stable clump of dark matter held together by its own gravity, but with no light, no heat, no fusion. They would be like ghostly, transparent stars drifting silently through the galaxy. If such objects exist, they could be detected through their gravitational effects, perhaps by the way they bend the light of stars behind them as they pass. The idea is still speculative, but it opens up a vision of the universe filled not only with a diffuse sea of dark matter, but also with these quiet compact objects, invisible stars, made not of fire, but of a cold, coherent wave, a frozen note in the cosmic symphony. The universe of actions is a place of gentle waves and silent hums, a reality that is less about individual particles and more about the collective rhythm of an ancient cosmic field still oscillating from the first moments of time. The great mystery of dark matter is not something that exists only in the farthest reaches of the cosmos, in distant galaxies, or in the echoes of the Big Bang. It is here. It is now. It is all around us. Our own galaxy, the Milky Way, is spinning within its own vast, invisible halo of dark matter, a sphere of influence that stretches for hundreds of thousands of light years in every direction, far beyond the most distant stars we can see. We are living inside this cloud. Our solar system, in its long, slow journey around the galactic center, is sailing through this unseen substance. It flows around us and through us, a constant silent river that has been part of our world since the Earth itself first formed. We have spent our entire existence bathed in this current, never feeling it, never seeing it, but shaped by its presence in ways we are only just beginning to understand. To imagine this river is to shift your perspective on the space around you. The emptiness of the night sky is not an emptiness at all. It is full. The dark matter halo of our galaxy is not a static uniform cloud. It has currents, eddies, and streams. As the Milky Way has grown over billions of years, it has absorbed smaller dwarf galaxies, pulling them apart with its gravity. The stars from these consumed galaxies are stretched out into long, faint ribbons called stellar streams, which still orbit within the halo today. But the dark matter from these smaller galaxies also remains, forming denser currents within the larger halo, a kind of river within a river. Our solar system may be passing through one of these streams right now, or it may have passed through them in the past. These streams would represent a slightly denser flow of dark matter particles, a subtle thickening of the invisible rain. Scientists are trying to map these streams by studying the motions of stars, hoping to predict when the Earth might pass through a denser patch, which could make the faint signal of dark matter easier to detect in our underground laboratories. The sky above is not just a dome of stars. It is a dynamic, flowing environment with a history written in invisible currents. This unseen river passes through the Earth as if it were not there. The planet's rock, its iron core, its deep oceans, none of these present any obstacle to a particle that does not know the electromagnetic force The Earth moves through the dark matter halo, and the dark matter halo moves through the Earth. But this passage is not entirely without effect. As the Earth orbits the Sun, and the Sun moves through the galaxy, our planet has a certain velocity relative to the great slow-moving cloud of dark matter. This means that from our perspective, there should be a dark matter wind, a steady, directional flow of particles coming from a specific direction in the sky. This wind would be incredibly subtle, but it should cause a seasonal variation in any dark matter signal we might detect. In one part of the year, as the Earth's orbital motion is aligned with the Sun's motion through the halo, we would be moving faster into the wind, and the signal should be slightly stronger. 6 months later, when our motion is opposed to it, we would be moving more slowly, and the signal should be weaker. This annual modulation is a key signature that scientists are searching for. It would be the ultimate proof that any signal they detect is not from some local source of radiation, but from the great unseen river of the cosmos itself. It would be the faint, seasonal breath of the galaxy, heard in the quietest chambers on Earth. And though these particles almost never interact, their sheer number means that over long periods, they can have subtle effects. One of the most beautiful and strange ideas is that dark matter could be captured by the gravity of massive objects like the Sun. A dark matter particle passing through the Sun might, on an incredibly rare occasion, interact with a nucleus and lose just enough energy to become gravitationally bound. It would then orbit within the Sun, slowly sinking toward the core. Over billions of years, a small but significant population of dark matter particles could accumulate at the center of our star. If these particles are their own antiparticles, as many WIMP theories suggest, they would begin to annihilate each other in the dense environment of the solar core. This annihilation would produce a small but steady stream of high-energy neutrinos particles that can escape the Sun and travel to Earth. And so, another search for dark matter is underway. Neutrino telescopes buried deep in the Antarctic ice or at the bottom of the sea are looking toward the Sun, searching for an excess of these energetic neutrinos. It is a way of using the Sun as its own dark matter detector, a giant net that has been patiently collecting these ghostly particles for eons. If we see this signal, it would be like seeing the sunshine in a new kind of light, a light born from the darkness at its heart. The presence of this vast, invisible substance around us might solve other smaller cosmic puzzles as well. For example, astronomers have long been puzzled by the orbits of certain wide binary stars, pairs of stars that orbit each other at great distances. In some cases, their orbits seem to be influenced by more gravity than the stars themselves can provide. Some have wondered if the pervasive presence of the dark matter halo could be exerting a subtle long-term influence on these delicate systems. Similarly, the way that stellar streams are stretched and shaped as they orbit the galaxy gives us a powerful tool to map the gravitational field of the halo. By measuring the positions and velocities of stars in these streams, we can reconstruct the shape and density of the invisible mass they are moving through. These streams are like cosmic breadcrumbs, tracing the unseen contours of the galaxy's gravitational landscape. They allow us to weigh the darkness, to map its hills and valleys, and to understand our place within it. We live our lives on the surface of a small, rocky planet, feeling anchored, feeling still. But we are travelers on a vast and silent river. This river of dark matter is not something to be feared. It is part of the natural order of the cosmos, as fundamental as gravity, as ancient as light. It is the substance that cradled our galaxy into existence, that holds our sun in its long, slow orbit, and that flows through us in this very moment, connecting us to the grand unseen whole. To lie still in the quiet of the night is to feel in some small way this motion. The turning of the Earth, the orbit around the sun, the great sweep through the galaxy, all of it happening within this gentle invisible current. We are not separate from the mystery. We are floating in the middle of it. The unseen river is our home. To find something that is defined by its invisibility, you must first find a place of perfect silence, a place so deeply shielded from the noise of the world that the faintest whisper can be heard. This is the guiding principle behind the search for dark matter, a quest that has taken scientists to some of the quietest, most isolated places on Earth. They have gone deep underground, beneath mountains, into abandoned mines, seeking a sanctuary from the constant rain of cosmic rays and other particles that bombard our planet's surface. For in these deep, still places, if a signal does appear, it is more likely to be something truly new, something from the invisible world that has passed effortlessly through the rock above. It is a search that requires not just technology, but a profound and patient stillness. Imagine descending deep into the earth, leaving behind the sunlight the sounds of the world, the busy hum of electricity. You travel through tunnels of rock a mile or more thick until you reach a cavern clean and bright, filled with a strange and beautiful machine. This is a direct detection experiment. The heart of the machine is often a large pristine crystal or a vat of intensely purified liquid such as xenon or argon. This material is the target. It is the net designed to catch a ghost. The entire apparatus is cooled to temperatures colder than deep space, just a fraction of a degree above absolute zero. At these temperatures, the atoms in the detector are almost perfectly still, their natural vibrations reduced to a faint quantum hum. This stillness is essential, for the signal they are hoping to detect is the gentlest of nudges, the hypothetical collision of a single dark matter particle with a single atomic nucleus. If a WIMP, having passed through the miles of rock above, were to enter this silent chamber and strike one of the nuclei in the detector, it would transfer a tiny amount of kinetic energy. This energy would cause the nucleus to recoil like a billiard ball struck by another. This recoil would in turn create a tiny fleeting signal, perhaps a minuscule flash of light, a small puff of ionization, or a subtle vibration, a phonon that ripples through the crystal lattice. To detect such a faint signal, the instruments surrounding the target must be of almost unimaginable sensitivity. Photomultiplier tubes, like 1,000 tiny eyes, wait in the darkness for a single photon to appear. Delicate sensors listen for a vibration that is less than the tremble of a single atom. And all of this is housed within layers of shielding copper, lead, water, plastic, each layer designed to stop any stray particles from the outside world that might mimic the signal of a dark matter interaction. It is an experiment built from layers of silence, a quiet heart protected by a shell of stillness, all waiting for a single rare event. For years, these experiments have run in the deep quiet, collecting data, listening. The silence has been profound. While some experiments have reported tantalizing hints, fleeting signals that appeared for a time and then vanished, none have yet found the clear, unambiguous evidence of a dark matter particle. The ghost has remained a ghost, but each new experiment has pushed the boundaries of our knowledge. With each year of silence, they have ruled out possibilities, narrowing the search, telling us what dark matter is not. They have placed ever more stringent limits on how strongly dark matter can interact with ordinary matter. This process of elimination is just as important as a discovery. It is like mapping a dark room by feeling for the walls. Each time we find a place where the wall is not, we learn a little more about the shape of the space. The search has become a testament to human patience, a long, quiet vigil kept in the heart of the earth on behalf of us all. And the challenges are immense. Even deep underground, the world is not perfectly quiet. The rocks themselves contain trace amounts of radioactive elements which can decay and produce particles that mimic a dark matter signal. The materials used to build the detectors can have their own faint radioactivity. Even the air in the laboratory can contain radon gas, which can interfere with the measurements. And so the scientists who build these experiments have become masters of purity. They use copper that has been stored underground for decades to shield it from cosmic rays. They develop new techniques to scrub their liquid targets of any impurities. They work in clean rooms like those used for building spacecraft to prevent a single speck of dust from contaminating their instruments. It is a pursuit of an almost impossible cleanliness, an attempt to create a small pocket of the universe that is purer and quieter than anything found in nature, so that the true signal, when it comes, will be unmistakable. This search for a flicker in the dark is not the only way we listen. Other experiments use different strategies looking for different kinds of whispers. For example, if dark matter is made of axions, the signal would not be a collision, but the conversion of an action into a photon in a strong magnetic field. So, these experiments consist of a resonant cavity, like the chamber of a musical instrument placed inside a powerful magnet. Scientists slowly tune the frequency of this cavity, sweeping through the possible masses of the axion, listening for a tiny resonant spike of power, a single, pure note appearing above the background noise. It is like tuning a cosmic radio, hoping to land on the one station that is broadcasting the signal of the invisible universe. The expected signal is so faint it would be like trying to hear a single snowflake land in the middle of a blizzard. And yet the search goes on, driven by the belief that with enough sensitivity and enough patience, we will eventually hear it. Whether we are listening for a collision or a conversion, a flicker or a hum, all of these searches share a common philosophy. They are attempts to meet the invisible world on its own terms. We cannot force dark matter to reveal itself. We can only build a space that is quiet enough, still enough, and patient enough for it to leave a trace of its passing. It is a deeply humble form of science. It is not about grand dramatic discoveries, but about the slow, patient accumulation of silence until what is left is the truth. And so, deep beneath our feet, in the silent, waiting dark, these beautiful and intricate machines continue their vigil. They are our ears pressed against the wall of reality, listening for a heartbeat we know must be there, but have not yet found. They are the quietest places on Earth, built to hear the quietest thing in the universe. While some listen for the whisper of dark matter in the deep and silent Earth, others search for its shadow in the oldest light of the sky. The hunt for this invisible substance is a tale of two frontiers, the incredibly small and the unimaginably large. And on the vast canvas of the cosmos, dark matter reveals its presence not through a fleeting touch, but through its grand and patient artistry, bending the light of ancient galaxies and sculpting the very patterns of the universe. To see dark matter with a telescope, you must learn to see what isn't there, to trace the shape of an invisible mountain by observing how the rivers of starlight flow around it. It is an act of cosmic cartography, mapping a hidden continent by the way it influences the visible shores. Our most powerful tool for this celestial survey is the phenomenon of gravitational lensing. As we have drifted through this idea before, the immense mass of dark matter warps the fabric of space-time, and light from distant objects follows these curves. The effect is like looking through a flawed and ancient piece of glass. The images of galaxies behind the lens can be stretched, magnified, and distorted into beautiful ethereal shapes. Astronomers use telescopes like the Hubble Space Telescope and the James Webb Space Telescope to take long, deep exposures of massive galaxy clusters, the great crossroads of the cosmic web, where dark matter is most concentrated. In these images, they find the faint, ghostly arcs of light from galaxies that lie billions of light years behind the cluster. These arcs are not physical objects. They are illusions, the stretched-out portraits of single galaxies whose light has been bent around the cluster's immense gravitational field. By carefully measuring the shape and curvature of these arcs, scientists can work backward. They can reconstruct the gravitational field of the cluster and create a map of its mass. And what these maps consistently show is that the vast majority of the mass is not in the bright visible galaxies. It is in a smooth, sprawling, invisible halo of dark matter that surrounds and permeates the entire cluster. The galaxies themselves are just the luminous peaks of a much larger unseen mountain range. These maps are our most direct visual evidence of dark matter's existence on a grand scale. They are portraits of the invisible, painted with the borrowed light of ancient stars. Each arc, each distorted smudge, is a brushstroke revealing the quiet, powerful presence that holds the cluster together. This technique is not limited to massive clusters. Even the halo of a single galaxy can act as a lens, though the effect is much more subtle. This is called weak gravitational lensing. It does not create dramatic arcs or rings, but instead produces a tiny, almost imperceptible distortion in the apparent shapes of the thousands of background galaxies behind it. A galaxy that should be perfectly round might appear slightly elongated. This effect is too small to be measured for any single background galaxy. But by averaging the shapes of tens of thousands of them, astronomers can detect a coherent pattern of distortion. It is a statistical whisper, a faint alignment in the shapes of distant galaxies that reveals the gravitational footprint of the invisible dark matter halo in the foreground. It is like detecting a gentle, invisible current in the ocean by observing the subtle alignment of thousands of tiny floating leaves. This method has allowed us to weigh the halos of distant galaxies, to study their shapes, and to confirm that the unseen river of dark matter is a universal feature of the cosmos present around every great city of stars. The oldest light in the universe, the cosmic microwave background, also carries the shadow of dark matter. As this faint, ancient glow has traveled toward us for over 13 billion years, its path has been gently warped by all the structures it has passed through the galaxy. Clusters, the filaments of the cosmic web, all of it held together by dark matter. This gravitational lensing of the CMB imprints a subtle pattern on the light, a faint swirling distortion in its temperature map. By studying this pattern, cosmologists can reconstruct the distribution of all the matter between us and the edge of the observable universe. It is the ultimate form of cosmic survey, using the light of the Big Bang itself as a backlight to illuminate the entire intervening structure of the cosmos. The results confirm our picture of a universe dominated by dark matter, its structure growing and evolving over eons, its quiet gravitational influence etched into the very fabric of the first light. And there is another more dynamic way to watch dark matter at work in the sky. By observing the motions of things, just as the speeds of stars within a single galaxy revealed the presence of a dark matter halo, the motions of galaxies within a cluster tell the same story on a grander scale. Galaxies in a cluster are not static. They orbit the cluster's common center of mass, moving at incredible speeds, thousands of kilometers per second. When astronomers first measured these speeds, they found that the galaxies were moving far too fast to be held together by the gravity of the visible matter alone. The clusters should have flown apart billions of years ago. The only way they could remain bound was if they were embedded in an immense cloud of unseen mass, a dark matter halo, 100 times more massive than all the stars and all the galaxies combined. It was one of the first pieces of evidence for dark matter discovered long before we could map it with gravitational lensing, and it remains one of the most powerful. The dance of the galaxies is a dance choreographed by an invisible partner. Even the way galaxies themselves are arranged tells a story. The cosmic web with its filamentary structure is a direct prediction of our theories of cold, slow-moving dark matter. This is because such a structure is what naturally emerges when a substance that only interacts via gravity collapses over billions of years. If dark matter were hot or fast-moving, it would have smoothed out these structures, creating large, diffuse blobs instead of intricate threads. The very existence of the cosmic web, the fact that galaxies are arranged in this beautiful interconnected pattern, is itself a powerful piece of evidence for the kind of dark matter we believe exists. The sky, when viewed on the largest scales, is a map of dark matter's nature. Its quiet, slow-moving character is written in the grand design of the whole. And so our gaze into the farthest light is a constant conversation with the darkness. We look for its shadow. We measure its weight. We watch its dance. We cannot see it, but we can see the universe it has built. And in every bent beam of light, in every orbiting galaxy, we find another quiet confirmation of its gentle and absolute dominion. While some search for dark matter in the silent depths of the Earth or the faint light of distant galaxies, another quest takes place in a world of pure energy and speed. It is a search that seeks not to find the dark matter that already exists, but to create it just for a fleeting moment in a flash of light and power that echoes the first seconds of the universe. This is the world of particle colliders, machines of immense scale and precision. Like the Large Hadron Collider, or LHC in Europe. These are not quiet places of patient waiting. They are arenas of controlled violence where we smash particles of ordinary matter together at nearly the speed of light, hoping that in the debris of these collisions we might catch a glimpse of something new, something that belongs to the invisible world. Imagine a vast circular tunnel buried deep underground miles in circumference. Inside, beams of protons are accelerated by powerful magnets, circling in opposite directions faster and faster until their energy is tremendous. Then, at precise points along the ring, these beams are made to cross, and a tiny fraction of the protons collide head-on. In that infinitesimal moment of impact, the energy is so concentrated that it recreates the conditions of the very early universe. According to Einstein's famous equation, E is mc2, energy can be converted into mass. And in these collisions, the kinetic energy of the protons is transformed into a shower of new exotic particles, many of which are unstable and decay in a fraction of a second. Surrounding the collision point are detectors of breathtaking complexity, layered like the petals of a giant mechanical flower, designed to track the path, energy, and identity of every particle that flies out from the impact. The search for dark matter at a collider is a search for something that is missing. If dark matter particles like WIMPs are created in a collision, they would not leave a trace in the detector. They would pass through the layers of sensors as if they were not there, carrying energy and momentum away into the unseen. But their absence can be detected. Physicists carefully measure the energy and momentum of all the visible particles that emerge from a collision. According to the laws of conservation, the total momentum before and after the collision must be the same. If the visible particles are all flying out in one direction, it implies that something else, something invisible, must have recoiled in the opposite direction to keep the balance. This missing energy is the signature of a particle that has escaped the detector. It is the footprint of a ghost. By looking for collisions with a significant amount of this missing energy, scientists can search for events where dark matter might have been created. This method is called indirect detection. We do not see the particle itself, but we infer its creation from the hole it leaves in our accounting. It is like watching a silent explosion. If you see all the debris flying to one side, you know that something must have propelled it, even if you did not see the cause. The search is painstaking. Billions of collisions happen every second, and the vast majority of them produce only familiar particles. The events that might signal dark matter are incredibly rare, perhaps 1 in a trillion. And so scientists use powerful computers and sophisticated algorithms to sift through this mountain of data, looking for the telltale sign of imbalance, the subtle hint that energy has been carried away into the invisible realm. It is a search for a needle in a haystack of cosmic proportions. The discovery of the Higgs boson at the LHC was a monumental achievement, confirming a key part of our standard model of particle physics. But the standard model is incomplete. It has no particle that can account for dark matter. This is why many physicists believe that new physics must lie beyond the standard model, and that colliders like the LHC are our best hope for discovering it. Theories like supersymmetry, which predicted the WIMP, also predict a whole family of new heavier particles. If these theories are correct, the LHC should be able to produce them. The hope is that among these new particles, we will find one that is stable, neutral, and weakly interacting, the perfect candidate for dark matter. So far, these new particles have not appeared. The silence from the colliders has been as profound as the silence from the underground detectors. But as with those experiments, the absence of a signal is still a form of knowledge. It rules out possibilities, it constrains our theories, and it pushes us to think in new and more creative ways about what dark matter could be. Perhaps dark matter is lighter than we thought, or interacts in ways we haven't predicted. Perhaps it is connected to a hidden sector of particles that only rarely communicates with our own. Or perhaps the energy of our colliders is not yet high enough to create it. And so physicists are planning for the future, designing even more powerful machines that can probe deeper into the fabric of reality, creating even more energetic collisions that come even closer to the moment of the Big Bang. Each new generation of colliders is a step further into the unknown, a journey into the heart of matter itself. These machines are our time machines, allowing us to recreate for a fraction of a billionth of a second the conditions of the infant universe, the very furnace where dark matter was forged. It is a strange and beautiful duality. To understand the largest structures in the universe, the galaxies and clusters held together by dark matter, we must create the smallest, most fleeting events in a laboratory on Earth. The macrocosm is reflected in the microcosm. The secrets of the galactic halo are hidden in the debris of a proton collision. The search for dark matter is a bridge between these two worlds. It is a reminder that the laws of physics are universal, governing the slow dance of galaxies and the frantic spark in a machine with the same elegant and mysterious rules. And in the controlled and fleeting fire of our colliders, we hope to ignite a spark of the darkness to bring it into being for just a moment, so that we may finally know its name. In the patient and ongoing search for dark matter, there are times when the universe seems to offer a hint, a quiet and ambiguous signal that flickers at the edge of our understanding. These are not the clear, definitive proofs we hope for, but anomalies, puzzles in the data that do not quite fit our expectations of the ordinary cosmos. They are like faint, unexpected notes in a familiar melody, making us lean closer and listen more carefully. These signals may in the end turn out to be nothing more than the whispers of known physics that we have not yet fully understood. Or they could be the first tentative echoes from the invisible world, the first signs that our long search is nearing its goal. We drift through these mysteries with caution, but also with a gentle sense of wonder. One of the most persistent and tantalizing of these anomalies comes from the very heart of our own galaxy. When astronomers use telescopes that can see high-energy light, such as gamma rays, they observe a diffuse glow coming from the center of the Milky Way. Much of this glow can be explained by known cosmic processes, pulsars spinning with incredible speed, cosmic rays colliding with interstellar gas, and the chaotic environment around the supermassive black hole at our galaxy's core. But when all of these known sources are accounted for, there remains a faint spherical excess of gamma rays, a subtle extra glow that has no clear explanation. What makes this signal so intriguing is that its properties, its energy, and its distribution in the sky match remarkably well with the predictions for what we would see if WIMP dark matter particles were annihilating in the dense environment of the galactic center. It looks in many ways like the faint fire from the mutual destruction of ghosts. For years, this galactic center excess has been a source of intense debate. Could this be it? The first indirect detection of dark matter. The possibility is thrilling, but the universe is complex, and there may be other explanations. Some astronomers have argued that the signal could be coming from a large undiscovered population of pulsars spinning too faintly to be detected individually, but whose collective gamma-ray emission could mimic the dark matter signal. It is a puzzle of cosmic forensics. Are we seeing the signature of a new fundamental particle, or simply the glow of thousands of dead stars we have not yet counted? Telescopes continue to watch, gathering more data, refining our models, hoping to distinguish the signal from the noise. For now, the excess glow remains a beautiful and unsettling mystery, a possible whisper from the dark that we cannot yet be sure we have understood. Another strange signal has come from the wider cosmos in the form of X-rays. In 2014, astronomers studying the light from distant galaxy clusters noticed a faint, unidentified spike of X-ray emission. It was a line in the spectrum that did not correspond to any known atomic transition. It was an orphan signal, a note of a frequency that no known instrument in the cosmic orchestra should be playing. This signal was seen in multiple galaxy clusters and even in our neighboring Andromeda galaxy. One of the most exciting possibilities is that this X-ray line could be the sign of a decaying dark matter particle. Perhaps dark matter is not perfectly stable, but over billions of years, a tiny fraction of it decays, releasing a photon of a specific energy. If this were the case, we would expect to see a faint line of that exact energy coming from any direction where dark matter is abundant. The 3.5 keV line, as it has come to be known, fits this picture tantalizingly well. But here too, there are other possibilities. It could be a faint atomic line from a known element that is behaving in unexpected ways in the hot gas of galaxy clusters. The debate continues with different telescopes and different teams of scientists finding conflicting results. The signal is so faint that it is difficult to separate from the background noise. It is another cosmic maybe, another echo that keeps us searching. And then there are the anomalies that come not from light, but from particles. For several years, orbiting detectors designed to study cosmic rays, high-energy particles from space, have measured a surprising excess of positrons, the antimatter equivalent of electrons. There are more of these positrons at certain high energies than our standard models of the galaxy can explain. This has led to speculation that these extra positrons could be another product of dark matter annihilation. Perhaps WIMPs in the galactic halo are annihilating and producing pairs of electrons and positrons. This would create a source of these antimatter particles spread throughout the galaxy, which could explain the excess we see. But again, there is a more mundane explanation. The excess positrons could be coming from nearby pulsars, which are known to accelerate particles to high energies in their powerful magnetic fields. Distinguishing between these two possibilities is incredibly difficult. It requires a precise understanding of how particles travel through the galaxy's magnetic fields, a process that is itself complex and chaotic. The positron excess is a footprint, but we do not yet know what made it. These anomalies are the breadcrumbs that keep the search for dark matter so vibrant and so full of hope. They are the subtle hints that we are on the verge of a discovery. But they also teach us humility. The universe is filled with complex and beautiful processes, and our understanding of them is still incomplete. What looks like a signal from a new and mysterious substance may simply be a new and beautiful aspect of the world we already know. Each of these puzzles has pushed us to refine our understanding of astrophysics, to build better telescopes, and to think more creatively. They are the friction that creates the spark of new knowledge, whether they turn out to be the first light from the dark sector or simply a deeper appreciation for the complexity of our own. These faint and fleeting signals are a gift. They are the gentle and persistent questions that the universe asks of us, inviting us to look closer, to listen more carefully, and to rest in the beauty of a mystery that is still slowly and gracefully unfolding. In the grand and orderly cosmos that dark matter seems to build, where every great city of stars is cradled in an invisible halo, there are exceptions. There are oddities. There are galaxies that seem to have broken the rules. In recent years, astronomers have discovered a handful of strange, faint galaxies that appear to have little to no dark matter at all. They are like ghosts that have lost their shadows. Their existence is a profound puzzle, a gentle but persistent challenge to our understanding of how galaxies are born and how they live. If dark matter is the essential scaffold for galaxy formation, the gravitational seed from which everything grows, then how can a galaxy exist without it? It is a question that opens up new and unexpected pathways in our exploration of the invisible universe. These strange galaxies are often faint, diffuse, and wispy. They are called ultra-diffuse galaxies, or UDGs. From our telescopes, they look like pale, scattered collections of stars, so spread out that you can see the more distant galaxies right through them. When astronomers first began to study them, they measured the speeds of the stars within them, expecting to find the same familiar signature of dark matter stars moving too fast to be held by the visible matter alone. But in a few remarkable cases, they found the opposite. The stars were moving slowly, exactly as they should, if the only gravity present was from the stars themselves. The invisible halo, the ghostly guardian that should have been there, was missing. It was as if someone had built a city, and then the land it was built on had vanished, leaving the buildings to float impossibly on their own. How can such a thing happen? One of the leading ideas is that these galaxies were not born this way, but were changed by a violent and traumatic past. Perhaps these galaxies were once normal dark matter-rich systems that passed too close to a much larger galaxy. In such a close encounter, the immense gravitational tides of the larger galaxy could have acted like a cosmic wind, stripping away the diffuse, loosely bound dark matter halo, while leaving the more compact central collection of stars intact. This process is called tidal stripping. The galaxy would have survived the encounter, but it would have been left naked, a collection of stars without its invisible anchor. It would then drift away, a fragile and lonely ghost, a refugee from a gravitational storm. Astronomers are now searching for other signs that might support this story, such as faint streams of stars or gas that might have been pulled away during the same encounter. Another possibility is even more dramatic. In the chaotic environment of a massive galaxy cluster, where hundreds or thousands of galaxies are all orbiting in a dense swarm, high-speed collisions can occur. If a small galaxy flies through the center of a much larger one, the friction from the gas and dark matter can have a powerful effect. It could be that the dark matter halo is more extended and more easily stripped away than the stars, which are more tightly bound at the galaxy's core. In this scenario, the galaxy would emerge from the collision bruised and battered, having left its dark matter ghost behind in the heart of the cluster. The existence of these dark matter deficient galaxies, particularly in dense cluster environments, seems to lend support to this idea. They are the survivors of cosmic traffic accidents, their strange nature a scar from their violent history. But there is another, more radical way to think about these galaxies. Perhaps they are not victims, but pioneers. Some theories of galaxy formation suggest that it might be possible under very specific conditions for a galaxy to form from gas that has been ejected from a galactic merger. In the collision of two large gas-rich galaxies, vast tidal tails of gas can be thrown out into space. It is possible that this gas could collapse to form a new galaxy, a tidal dwarf galaxy, that is born with very little of the parent galaxy's dark matter. It would be a recycled galaxy built from the leftover material of a cosmic collision, a child of ordinary matter alone. If such galaxies exist, they would be incredibly important, for they would show us that dark matter is not always a prerequisite for galaxy formation. They would prove that ordinary matter, on its own, can sometimes gather and light up the darkness. The discovery of these strange systems has also added a new and interesting twist to the debate about the nature of dark matter itself. For a long time, a small but persistent group of scientists has wondered if dark matter is even real. They have proposed alternative theories of gravity, known as modified Newtonian dynamics, or MOND, which suggest that gravity simply behaves differently on galactic scales. In these theories, there is no dark matter. The fast-spinning stars are explained by a stronger law of gravity. For a long time, these theories struggled to explain the universe on larger scales, like in galaxy clusters. But the existence of a galaxy without the effects of dark matter presents a challenge to MOND as well. If gravity is simply modified, then that modification should be universal. Every galaxy should show the effect. A galaxy that behaves in a perfectly normal Newtonian way is just as puzzling for MOND as a galaxy without dark matter is for the standard model. In a strange way, the discovery of a galaxy that seems to lack dark matter has become one of the strongest pieces of evidence that dark matter is a real physical substance. A substance that can on rare occasions be separated from the luminous matter we see. And so, these pale wispy galaxies, these ghosts that have lost their shadows, are not just cosmic curiosities. They are crucial laboratories for testing our deepest ideas about the universe. They are the exceptions that prove the rule, or perhaps the exceptions that show us the rule is more complex than we ever imagined. They remind us that the universe is not a uniform, predictable machine. It is a place of history, of accidents, of interactions. It is a place where galaxies can be born live and be transformed by their encounters with their neighbors. To look at one of these faint, transparent galaxies is to see a story of survival of loss and of the profound and mysterious relationship between the light and the darkness. They are a quiet testament to the fact that even in the vast and silent cosmos, nothing is forever. Even a ghost can be lost. As our journey through the invisible cosmos continues, we drift from the grand scale of galaxies to the smaller, more intimate corners of the universe, wondering if the gentle, pervasive presence of dark matter leaves its mark not only on the great cosmic web, but also on the individual worlds within it. Does this unseen river, flowing through everything, subtly shape the lives of stars and planets? Does it leave faint, almost imperceptible fingerprints on the familiar objects of our sky? These are questions at the very edge of our knowledge, ideas that are more like dreams or poetry than established science. But in the quiet of the night, it is a gentle thing to wonder, to imagine the subtler ways that the darkness might touch the light. One such dreamlike idea is that dark matter could change the lives of stars from within. Just as dark matter particles can accumulate at the center of the sun, they could do the same in other stars throughout the galaxy. In most stars, this would have a negligible effect, but in the very first stars to exist, the story might have been different. These first stars, called population 3 stars, were born from the pure hydrogen and helium of the early universe. They are thought to have been colossal, hundreds of times the mass of our sun, burning incredibly hot and living for only a few million years before exploding in spectacular supernovae. But what if they formed in the very densest regions of the first dark matter halos? In that environment, they would have captured a huge amount of dark matter as they formed. If this dark matter was the kind that could annihilate with itself, it could have created a new source of energy at the star's core, a kind of dark light burning alongside the nuclear fusion. This extra energy source could have had a profound effect. It might have made the stars puffier, cooler, and longer lived than they otherwise would have been. Instead of burning out in a few million years, these dark stars, powered in part by dark matter annihilation, might have survived for hundreds of millions of years, growing to even more immense sizes. We have never seen such a star. They would have existed only in the universe's distant past. But the James Webb Space Telescope is now peering so far back in time that it might just catch a glimpse of these first strange stellar objects. To find one would be to find a star that was a hybrid, a bridge between the visible and the invisible world, its heart glowing with the fire of both ordinary matter and the gentle, persistent annihilation of the darkness. And what of the end of a star's life? When a massive star collapses, it can form a neutron star, an incredibly dense, city-sized ball of nuclear matter. These objects have immense gravitational fields. Like the sun, they too could capture dark matter particles from the galactic halo. Over billions of years, a significant amount of dark matter could accumulate inside a neutron star. What happens then is a matter of intense speculation. If the dark matter particles are heavy enough, they could eventually collapse under their own gravity, forming a tiny black hole at the center of the neutron star. This black hole would then begin to consume the neutron star from the inside out quickly and catastrophically. The neutron star would simply vanish, leaving behind only a small black hole. Could this be a hidden death mechanism for old, isolated neutron stars? It is a chilling and beautiful thought that a star could be devoured, not by an external enemy, but by the slow, patient accumulation of the invisible substance it has been collecting its entire life. The influence of dark matter might extend to planets as well. Our own planet Earth is constantly moving through the dark matter halo of the Milky Way. As we've imagined, billions of these particles pass through us every second. The chance of an interaction is incredibly small, but not zero. Over the course of a year, a few dark matter particles might just happen to collide with nuclei in the Earth's interior. Each collision would deposit a tiny amount of energy, warming the planet by an infinitesimal amount. The total effect of this warming is thought to be completely negligible, far, far less than the heat from the sun or from the radioactive decay in the Earth's core. And yet, it is there. A constant, subtle source of heat from the cosmos, a gentle and persistent reminder of the river we are all floating in. Some have even wondered in the most speculative of moments if this energy could over geologic time have any effect on the Earth's internal dynamics, perhaps subtly influencing the currents in the molten core or the motion of tectonic plates. It is a thought at the very edge of possibility, a faint whisper that connects the deepest parts of our planet with the deepest mysteries of the galaxy. And there is another stranger idea. Some theories suggest that dark matter might not be a single, simple particle, but a whole dark sector, a rich and complex family of particles with its own forces, its own dark chemistry, just as our visible world has. In this picture, dark matter would not be just a diffuse, featureless cloud. It could form its own structures. Dark atoms, dark molecules, perhaps even dark planets, and dark stars, all interacting via forces we cannot perceive. This dark world would coexist with our own occupying the same space, but completely invisible to us, its presence felt only through the gentle tug of its gravity. Could a dark matter planet be orbiting our sun unseen? It is highly unlikely, as its gravity would have been detected by now. But the idea that the universe could contain a parallel reality, a whole shadow biosphere woven into the fabric of our own, is a profoundly humbling and wondrous thought. It would mean that the universe we see is only half the story, and that an entire, equally complex world of darkness lives silently alongside us. These are the dreams of physics, the poetic what-ifs that dance at the boundaries of our knowledge. They may or may not turn out to be true, but they serve a gentle purpose. They stretch our imagination. They remind us that the universe is not only stranger than we imagine, but stranger than we can imagine. And they allow us to see the familiar world, the sun, the earth, the stars, in a new light. We see them not as isolated objects, but as participants in a grander, more mysterious cosmic dance, their lives and deaths, perhaps subtly touched, gently shaped by the quiet, pervasive, and ever-present darkness. In our long and gentle journey through the invisible cosmos, we have rested in the idea that the universe is filled with a mysterious, unseen substance. We have given it a name, dark matter, and we have imagined what it could be: shy, heavy particles, or light cosmic waves. But what if the darkness we are trying to understand is not a substance at all? What if the ghost is not in the machine, but in the rules that govern the machine? This is the starting point for a different kind of exploration, a path less traveled in the search for understanding. It is the idea that the missing gravity we observe in galaxies is not from missing matter, but from a misunderstanding of gravity itself. It is a quiet, radical thought. Perhaps the darkness is not a thing, but a law. This alternative idea is known as modified Newtonian dynamics, or MOND. It was first proposed as a gentle but profound tweak to the familiar laws of gravity that we have known for centuries. Newton's law of gravity works perfectly for describing the motions of planets in our solar system, the falling of an apple from a tree, the orbits of moons. But as we have seen, it seems to fail on the scale of galaxies. Stars on the outer edges move too fast. Mond suggests that this is not because of an invisible halo of dark matter, but because gravity itself behaves differently where it is very weak. The theory proposes that in regions of extremely low acceleration, such as the faint gravitational environment at the edge of a galaxy, the force of gravity becomes slightly stronger than Newton's law would predict. It doesn't fade away as quickly with distance. This small change, this subtle strengthening of gravity's reach in the great emptiness, would be just enough to hold on to those fast-moving stars, keeping them in their orbits without the need for any extra unseen mass. To imagine this is to see the universe not as a space filled with matter, but as a space governed by a more nuanced and elegant law. In this picture, there is no ghost. There is only a deeper understanding of the force that shapes everything. Mondi has had some remarkable successes. It has been able to predict with surprising accuracy the rotation speeds of stars in a wide variety of spiral galaxies, often with more precision than dark matter models. It seems to capture a deep relationship between the visible matter in a galaxy, the stars and gas, and the total gravitational force. This is something that dark matter models where the amount of dark matter can be adjusted sometimes struggle to do. For the followers of MOND, this is a powerful sign that they are on the right track. It feels like the universe is whispering a simpler, more elegant truth. However, this different kind of darkness is not without its own deep shadows. While MOND works beautifully on the scale of individual galaxies, it has struggled to explain the universe on larger scales. In massive galaxy clusters, for example, MOND alone is not enough. Even with a modified law of gravity, there still seems to be a need for some extra unseen mass to hold the clusters together. It may not be as much mass as the standard dark matter model requires, but something invisible still seems to be there. Proponents of Mondi have suggested that this missing mass could be something more ordinary, like vast clouds of neutrinos, but no single solution has been entirely convincing. Furthermore, Mondi, in its original form, cannot explain the beautiful and intricate patterns of gravitational lensing that we see around these clusters, a phenomenon that dark matter models explain so naturally. And perhaps most profoundly, MOND struggles to tell a complete story of the universe's beginning. Our standard model of cosmology built upon the idea of dark matter provides a beautiful and coherent narrative of how the universe evolved from the Big Bang to the present day. It explains the tiny fluctuations in the cosmic microwave background and how they grew into the cosmic web. A theory of modified gravity must also be able to tell this story. And for a long time, Mond could not. It was a theory of how galaxies behave now, not a theory of how the universe began. In recent years, physicists have developed more complex relativistic versions of MOND that attempt to bridge this gap to weave a modified law of gravity into the grand tapestry of Einstein's general relativity and the expanding universe. These theories are mathematically complex, and none have yet been universally accepted. The path of modified gravity is a difficult one, for it requires not just adding a new particle, but rewriting the fundamental rules of the game, and so the scientific community remains divided. The vast majority of physicists and astronomers are confident that dark matter is the answer. The evidence from so many different sources, from the CMB, from gravitational lensing, from the cosmic web, all seems to point to to the existence of a new, real, physical substance. The standard model of cosmology with dark matter at its heart is a towering achievement, a story that holds together with remarkable consistency. For them, MOND is an interesting curiosity, a clever idea that works surprisingly well in some cases, but ultimately fails to explain the whole picture. It is a solution that is too simple for a universe that is too complex. But for the small and dedicated community of researchers who explore these alternative ideas, Mondi is a reminder that we should not be too certain in our knowledge. It is a call to question our assumptions, to look for elegance and simplicity, and to remember that there have been times in the history of science when our understanding of gravity has had to be revised. From Newton to Einstein, our picture of this fundamental force has deepened and changed. Perhaps they suggest there is another change yet to come. Perhaps the darkness is not a substance to be found, but a principle to be understood. This different path through the mystery is a testament to the creativity and persistence of the human mind. It shows us that there is more than one way to ask a question, more than one way to be in awe of the cosmos. And whether dark matter turns out to be a particle or a law, the journey of exploration itself, with its debates, its puzzles, and its moments of quiet wonder, is a beautiful thing. It is the universe in all its mystery, slowly and through many different voices, coming to know itself. In the quiet theater of our cosmic imagination, there is another stranger possibility for what the darkness might be. It is an idea that reaches back to the very first moments of time, to a universe so hot and so dense that the laws of physics themselves were different. It is the idea that dark matter might not be a new, undiscovered particle at all, but something far more familiar, yet in a form we have never seen. This is the story of primordial black holes. It is the suggestion that the invisible substance holding our galaxies together is made of countless tiny, ancient, and silent shadows born in the fire of the Big Bang and drifting through space ever since. A black hole is a region of space-time where gravity is so strong that nothing, not even light, can escape. Most of the black holes we know of are stellar mass black holes formed from the collapse of massive stars at the end of their lives. Or they are supermassive black holes, the giants that live at the centers of galaxies grown over billions of years. But in the first second after the Big Bang, the universe was a chaotic, turbulent place. The density of matter and energy was not perfectly uniform. There were tiny random fluctuations regions that were slightly denser than their surroundings. In such an extreme environment, it is possible that some of these overly dense regions could have collapsed directly under their own immense gravity, forming black holes without ever having been a star. These would be primordial black holes. Unlike their stellar cousins, these primordial black holes could have a vast range of masses. Some could have been as massive as thousands of suns, and these might have served as the seeds for the supermassive black holes we see today. But others could have been incredibly small. Some could have had the mass of a mountain compressed into a size smaller than a proton. Others could have had the mass of an asteroid, or a moon, or even a planet. The universe, in its first fiery moments, could have been seeded with a whole population of these tiny dark objects. And because they are black holes, they would be completely invisible, interacting with the rest of the universe only through their gravity. They would be in every sense of the word dark matter. To imagine a universe filled with these primordial shadows is to see the galactic halo in a new light. It would not be a smooth, continuous cloud of particles, but a swarm. A vast, scattered collection of discrete, compact objects ranging in size from the microscopic to the planetary. Each a tiny, perfect sphere of warped space-time, a relic from the beginning of time. They would be drifting silently through the galaxy, their individual gravitational fields too weak to be noticed, but their collective mass providing the immense weight needed to hold the stars in their orbits. The river of dark matter would not be a river of water, but a river of stones. This idea has a certain elegance. It does not require the invention of new, undiscovered particles or new forces. It uses the physics we already know, Einstein's theory of gravity, and applies it to the extreme conditions of the early universe. It suggests that the solution to the dark matter mystery might have been hiding in plain sight all along, a consequence of the universe's own chaotic birth. For many years, this idea was considered a fringe possibility. There were strong constraints on how many of these primordial black holes could exist. If there were too many of a certain mass, we should have seen their effects by now. For example, if they were common, they should occasionally pass in front of a distant star, and their gravity would briefly magnify the starlight in a characteristic way, an effect called microlensing. Searches for this effect have been done, and they have ruled out primordial black holes in a certain mass range as being the dominant form of dark matter. But recently, the idea has seen a quiet resurgence. The discovery of gravitational waves from merging black holes by observatories like LIGO has opened a new window onto the cosmos, and some of the black holes that LIGO has seen have masses that are slightly puzzling. They are heavier than what is easily explained by the collapse of single stars. This has led some scientists to wonder if these could be primordial black holes, or perhaps the result of mergers of smaller primordial black holes. The data is still very new, and there are other more conventional explanations. But it has reopened the door to a beautiful and strange possibility. What if the faint chirping signals of gravitational waves that we are now detecting from across the universe are the sound of the primordial shadows themselves colliding and merging in the deep darkness between galaxies? If dark matter is made of these objects, it would change the way we search for it. The deep underground experiments, waiting for the gentle nudge of a wimp, would never see a signal. A primordial black hole is far too large and far too rare to ever pass through a detector on Earth. But we could search for them in other ways. We could look for the faint ripples in space-time that they create as they move. We could look for the subtle ways they might bend the light of stars. We could even look for the faint glow of radiation that the very smallest of them might emit. According to Stephen Hawking, black holes are not completely black. They can slowly evaporate over immense timescales, releasing a faint thermal glow known as Hawking radiation. For a primordial black hole with the mass of a mountain, this process would be very slow, but it might just be detectable as a faint background of gamma rays. The search for dark matter would become a search for these ancient dying embers, the last faint whispers from the universe's first fire. The story of primordial black holes is a story of shadows. It is a vision of a universe populated by the ghosts of its own beginning. A cosmos where the darkness is not a diffuse sea, but a scattered population of perfect, silent spheres of gravity. It is a reminder that even the most familiar concepts, like a black hole, can take on new and strange forms in the crucible of the early universe. Whether this beautiful idea turns out to be true or not, it serves as a gentle expansion of our imagination. It allows us to dream of a universe that is not only filled with an invisible substance, but a substance that is itself structured, ancient, and born from the very collapse of space-time. It is a darkness that is not empty, but full of tiny, perfect, and eternal nights. And so our long, slow drift through the invisible cosmos comes to a gentle close. We have wandered through the silent architecture that holds the stars. We have listened for whispers from the beginning of time, and we have imagined the strange and beautiful possibilities of what the darkness might be. We have journeyed from the spinning heart of our own galaxy to the faintest light at the edge of seeing, and in every place we have found the same quiet, persistent, and profound mystery. The universe, in its grandest and most fundamental nature, is mostly unknown to us. The world we see, the world of light and color and form, is just the delicate, luminous surface of a reality that is far deeper, far vaster, and forever beyond the reach of our eyes. We do not have the answers. We do not know if the darkness is made of shy, heavy particles or light cosmic waves. We do not know if it is a sign of a deeper law of gravity or a scattered sea of ancient primordial shadows. The search continues in the deep quiet of the earth and in the patient gaze of our telescopes. But tonight, the search can rest. For the purpose of our journey was not to solve the mystery, but to find a sense of peace within it. It was to learn to see the darkness not as an emptiness to be feared, but as a presence to be respected. A quiet, gentle, and essential part of the whole. The existence of dark matter is not a flaw in the universe. It is a feature. It is the patient gravitational heart that allowed the cosmos to build, to create, to blossom with light. It is the invisible soil from which the galaxies grew. It is the silent river that guides our sun on its long journey through the Milky Way. It is the steady, unseen hand that holds the worlds together. To know this is to feel a sense of connection not only to the bright things we can see, but to the vast, quiet whole that we cannot. It is to understand that we are part of a story that is so much larger than ourselves. A story written in a language that is mostly silence. As you lie here now, at the edge of sleep, feel the gentle weight of your own body. That feeling of mass of presence is the same force that dark matter knows. Gravity is the one language that all matter speaks. It is the thread that connects you in this quiet room to the great invisible halos of distant galaxies. The same force that holds you gently to the earth is the force that choreographs the cosmic dance. You are not separate from this mystery. You are a part of it. The atoms in your body were forged in stars that were themselves cradled into existence by the gravity of the darkness. You are a child of both the light and the dark. And so let the questions fade. Let the names, the wimps, the axions, the halos dissolve into the gentle quiet of your mind. They are just the words we use to touch the edge of a great and beautiful unknown. What matters is not the names, but the feeling of wonder, The sense of peace that comes from accepting that we live in a universe that is still and may always be full of secrets. There is a deep comfort in that. It means there will always be more to discover, more to be in awe of. It means the story is not over. Let your breath be slow and steady. With each exhale, let go of the need to know. Let go of the day. Let go of the world of light and noise. And feel yourself drifting into a space that is quiet and full and safe. A space like the great gentle darkness of the cosmos itself. It is not an emptiness. It is a presence. It is the space in which all things rest. The stars are resting in it. The galaxies are resting in it. And now you can rest in it too. Sleep well and dream softly of the beautiful, invisible world that holds us all. And so we have journeyed to the edge of seeing, and in the deep quiet of the cosmos, we found a presence that asks nothing of us but to acknowledge its gentle weight. The stories and reflections we share here are created for educational and inspirational purposes. Gentle thoughts to hold as you drift into the quiet of your own inner world. As we let the cosmic facts dissolve like sugar in water, what remains is not a set of equations or theories, but a feeling. A sense of wonder, of humility, and of a deep and profound connection to something vast and unseen. And perhaps in this feeling there are lessons for us, not lessons to be studied or memorized, but truths to be held softly, like a smooth stone in the palm of your hand as you make your own quiet journey toward rest. Perhaps the first and most gentle lesson that dark matter offers us is a new way of seeing value. We live in a world that celebrates the bright, the loud, the visible. We are drawn to the brilliant stars, the luminous galaxies, the things that announce their presence with light and energy. We measure success in things that can be seen, counted, and displayed. And yet the universe tells us a different story. It whispers to us that the vast majority of what is real, what is essential, is completely invisible. The darkness is not an emptiness. It is the foundation. It is the silent, steady presence that gives the stars a home, that holds the galaxies in its gravitational embrace, that allows the beautiful shining structures of the cosmos to exist at all. And so, it is perhaps with our own lives. We so often judge ourselves and others by what is visible, the accomplishments, the appearances, the words that are spoken. But the truest and most essential parts of a person are often quiet, unseen. The kind near us that is given with no expectation of reward. The patient work that is done in silence long before any result appears. The resilience that is forged in quiet moments of struggle unseen by the world. The deep inner world of thoughts and dreams and hopes that gives a life its true shape and substance. Like dark matter, these things have a weight, a gravity. They hold a person together. They shape the world around them in subtle but profound ways. This is a quiet invitation to honor the invisible both in ourselves and in others. To know that our worth is not measured only by the light we give off, but also by the quiet, steady gravitational presence we offer to the world. It is a reminder to be gentle with ourselves, to know that even when we feel unseen, we have a substance, a value that is real and essential, holding our own small universe together. The universe also teaches us about the nature of connection. The one language that all matter speaks both light and dark is gravity. It is a gentle, persistent, and universal force. It is not a violent explosion or a brilliant flash, but a slow, steady, constant pull, a relationship that exists across the vastest distances. Dark matter shapes the universe not through force, but through this quiet, relational pull. It is the interconnectedness of all things made manifest. And in our own lives, we too are held together by invisible forces, by gentle gravities that are just as real. The bonds of love, of friendship, of family, of community. These are the dark matter of our human world. They are often silent. They are often taken for granted. They cannot be seen or measured in any simple way. And yet, they are the scaffolding upon which our lives are built. Think of the person whose quiet, steady presence in your life has held you in a safe orbit. Think of the community that gives you a sense of belonging. Think of the history, the ancestors, the stories that have shaped you, a gravitational pull across time. These connections are what give our lives structure, meaning, and stability. Like the dark matter halo of a galaxy, they keep us from being flung off into the void of loneliness and despair. To rest in this thought is to feel a sense of profound gratitude for these invisible ties. It is to recognize that we are not isolated stars, but part of a great interconnected cluster, held together by forces we can feel, even if we cannot always see them. And it is an invitation to contribute our own gentle gravity to the lives of others, to be a quiet, steadying presence, a source of connection in a world that can sometimes feel disconnected and chaotic. And then there is the lesson of humility, the peace that comes from embracing mystery. We have spent our journey exploring a substance that makes up most of the matter in the universe, and yet we do not know what it is. For all our science, for all our powerful instruments, the universe's greatest secret remains a secret. And there is a strange and beautiful comfort in that. We live in an age that prizes answer certainty and control. The unknown can feel like a failure, a problem to be solved, a darkness to be illuminated. But dark matter invites us to a different perspective. It invites us to see the unknown not as a void, but as a sacred space. A space for wonder, for curiosity, for awe. To accept that the universe is mostly a mystery is to let go of the need to have everything figured out. And to let go of that need is to find a deep and abiding peace. It is the same in our own lives. We cannot know the future. We cannot fully understand the hearts and minds of others. We cannot even sometimes understand our own. There will always be a darkness, an unknown at the heart of our experience. And we can struggle against it, or we can learn to rest in it. We can learn to see the mystery, not as a threat, but as an invitation to be present, to be open, and to be humble. The existence of dark matter is a cosmic reassurance that it is okay not to know. The universe is not asking us to solve it. It is simply inviting us to be a part of it, to look up at the night sky, and to feel a sense of wonder that is deeper and richer because of the secrets it keeps. As you drift toward sleep, you can let go of the questions of your day. Let them dissolve into the great gentle mystery. There is peace in the unknown. Finally, there is the lesson of the quiet creator. Dark matter was the patient architect of the cosmos. It was not the star, not the brilliant shining object that drew all the attention. It was the scaffolding. It was the foundation. It was the silent, invisible presence that created the conditions for the light to be born. It did its work in the darkness, slowly, patiently, over millions of years, building the structures that would one day become the beautiful, luminous galaxies. There is a profound beauty in this role. It is a reminder that the most important work is not always the most visible. It is a celebration of the quiet supporter, the gentle foundation, the one who creates a space for others to shine. In our lives, we will all have moments to be the star, but perhaps our truest, most meaningful purpose is found in being the dark matter for others. To be the steady, supportive presence that allows a friend to thrive. To be the quiet, unseen foundation of a family. To be the patient, humble contributor to a community doing the work that is not glamorous but essential. There is no ego in this role. There is only a deep and quiet sense of purpose. It is the joy of knowing that you are helping to build something beautiful, something that will shine long after your own small contribution is forgotten. To be the halo that cradles a star is a sacred task. And as you rest, you can think of the ways you have been the scaffolding for others, and the ways others have been the scaffolding for you. It is the most beautiful and invisible of all human exchanges, the quiet gravity of care that holds our worlds together. So let these thoughts be like a soft, dark blanket covering you in a sense of peace. The universe is vast, and you are a small but essential part of it. You are made of the same stardust as the brightest suns, and you are held by the same gentle, invisible gravity as the greatest galaxies. You are a being of both light and dark, seen and unseen. And there is a profound and beautiful balance in that. Rest now in the heart of this great mystery. Let the silence of the cosmos be your lullaby. Let the gentle pull of gravity be your comfort. There is nothing more you need to understand. There is only this moment of quiet and of peace. Sleep well, and good night.